it's okay. I can use this one, no problem. Okay. Thank you very much. Good afternoon. Today, I would like to show you what we're doing at the University of Bologna in collaboration, of course, with other colleagues from the University of Cagliari and the University of Kentucky, in terms of printing small molecules to create radiation sensors that are capable to detect ionizing radiation, that is, X-rays or, in general, gamma rays. So first of all, why is it interesting? Because we got high energy radiation in many applications, and the interest for a plastic or a flexible, low-cost, thin detector is very big. Why? Because we do need low-power supply portable detectors, conformable. Think about applications in the medical field, or easily with a low weight, so that they can also be used against for space applications. Why are we working with organic materials and small molecules? First of all, because of course they can cover with low-cost large areas, starting from solutions, so they can be also scaled up in large numbers over large areas. They're lightweight and flexible, but the two very interesting properties are that their properties can be easily tuned by chemically modifying the molecule structure. The second one is that they have a low Z. The density is very low, but also the atomic number is low because they are composed mostly of carbon, hydrogen, and oxygen. So their absorption with respect to ionizing radiation is very similar to the human tissue. And that is very important for medical dosimetry application. So, very briefly, what is the state of the art in radiation detectors? There are two approaches, indirect and direct detection. In the indirect detection, you use a scintillator that converts the incoming X-ray photons into visible photons, and you couple it to a photodetector that detects the visible photons, transferring the charge into an electron hole pairs. The direct detection is carried out with a material that directly transforms the incoming X-ray photons into an electron hole pair. We work with this approach, so we want to directly convert the X-ray photons into an electron hole pair. So as you can imagine, it's a kind of faster and simpler process. There are examples, but very recent, of organic material used as direct radiation detectors, because historically, organic materials have been used for the indirect detection. So they were used for scintillators, and also now we know there's quite a lot on organic photodiodes based on printed transistors and OPD. Now what we want to do is to use organic small molecule materials to directly detect the radiation. There are examples of blends with between polymers, bulk heterojunction, added with the materials, nanoparticles or structures that have a high Z to increase the absorption of the very thin layer of the desired radiation. We work with thin films. That's another important feature, and that's what I'm presenting you today, because we believe, again, that if we want to go for printed and flexible, we have to go and stay thin. So we work with the TIPS-pentacene solution deposited that gives place to multicrystalline, polycrystalline, very thin film. The crystalline thickness is about 150 nanometers. They're thick, they're thin and long. And we just produce them by drop cast into a very simple PET substrate onto which an interdigitated gold source and drain two-terminal device have been patterned. And what is really interesting is that if you measure the photocurrent during an on-off switching X-ray beam, and the energy of the beam is the one typically used for mammography, so it's really a standard medical probe, you can get a very nice photocurrent induced with a bias voltage as low as 0.2 volts. That is very interesting, also because you can improve this result, of course. By the way, the response is linear and scales with the dose rate, and that is the very important feature that you need, and I will show you in a minute, to make a real dosimeter good for practical uses. How can you improve this very simple two-terminal device? Well, we use the transistor as a bottom structure with a very thin gate dielectric so that, of course, it stays flexible, but also the voltage, the operating voltage, remains relatively low. That is interesting because, as you can see, if we operate it with the on-off switching X-ray beam, we see indeed the photocurrent going up and down. The different curves refer to different dose rates, so it's the intensity of the X-ray beam arriving on the sample. Why is there an advantage of using a transistor? Yes, the advantage is that you can control the on-off state of the sensor. So basically, by controlling with the gate voltage, you can switch the sensor off, or you can switch it on and increase the sensitivity because you control the amount of carriers in the channel. In this way, we manage to obtain sensitivity values that are very, very good compared to what are the standard values for polymeric films that have been added with nanoparticles, or even with organic single crystals that need to be operated, though, at several tens of volts. So that was an interesting set of results that prompted us to think, why is it working? Because if you interpret this result in terms of classical silicon or gallium arsenide photon to electron conversion, it doesn't work because the absorption rate is so small that, of course, you cannot simply think that every photon will just generate that number of electron pairs. So why is it working? Is because there is a photoconductive gain effect taking place. What is this effect? It's known also in the organic photodiode community. When X-rays arrive onto a thin organic small molecule film, basically they do generate electron hole pairs, but the films contains a large number of traps, in particular electron traps, that make the material, usually in this case TIPS-pentacene, a p-type conductor. And so electrons are trapped and holes need to be constantly emitted from the source to the drain in order to maintain charge neutrality. And so what happens is that as long as the electron stays trapped, we have a gain induced by the extra number of positive charges that have to be injected again to maintain charge neutrality. This is can be nicely modeled, and it works very, very well if we consider two contributions to this gain. And the two contributions are given by the carrier lifetime term, this one, and a transit time term. The ratio between these two provides the gain. As you see, the bottom term is mostly related to the mobility and the geometry of the device, while the top term relates to the charge density and alpha and gamma, two parameters related to the trapping effects of the traps. So the idea is, if we want to keep, now that we've understood a bit about how and why these thin films work as radiation X-ray detectors, and we want to keep them as flexible and large area sensors that have this very good human tissue equivalency, we have to do something about the fact that they have a very, very low absorption. So it is indeed good for the human tissue issue, but we have to improve it if we want the efficiency of the single pixel to be decent. So there are basically three approaches that we think can be used to improve this efficiency and enhance the efficiency of the single pixel. The first one, of course, is to increase and enhance this photoconductive gain effect. And how can we do it? We can act on the absorption rate by increasing basically the Z elements inside the material, or we can increase the other factor contributing to the overall gain that is improving the transport properties of the film, improving the quality, the mobility, and the control of the charge transport. So today I will just focus, we're trying basically all these approaches, but I think what is a really interesting one is the one I will just show you today, which is increasing the Z number of the thin film by tailoring the composition of the molecule. So the idea is that we're not adding extra nanoparticles or elements, making it a blend. We leave it a pure small molecule organic film, but basically we use TIP germanium pentacene instead of TIPS. So what John Anthony from the University of Kentucky did was simply to substitute the silicon atom with the germanium atom in the molecule. The result is very interesting if you look at the attenuation fraction in the graph on the right-hand side. You see that already by adding this by swapping the silicon atom with the germanium one, the absorption coefficient and the attenuation fraction go up very, very much. So the idea, we have about an order of magnitude higher attenuation fraction. So we started working with this molecule. We deposited same with the drop cast on this identical transistor substrate, these thin films in a polycrystalline form. And we measured the mobility and the transport properties of these devices that are quite good. If we compare it with the silicon, with the TIPS-pentacene one, we see that the TIPS are basically at worse performance than on average the TIP germanium one. So that means the transport properties and the quality of the film is definitely good, if not better, than the TIPS one that we've been using so far. What happened once we put and tested these new films as X-ray detectors? As you see, the on-off X-ray response goes on very nicely. And just another comment that I didn't do. It's really good because you see they're reproducible and the baseline does not drift, and that is the advantage of using the transistor structure. What is less good is the fact that you see they're very long in reaching saturation, and also the decay time is very long. And that is due to the photoconductive gate process, because being a trapping and detrapping process, it takes time. That is related to the trapping time of the charge. But this should not discourage the use of this material, because in general, one does not really need ultra-fast exposure time to detect radiation. Only in peculiar application like CT scans, you need ultra-fast flashing on X-ray detection. And secondly, I will show you in a further slide that also if you work at a fast rate of exposure, so with very, very short exposure, these devices are capable of detecting. What will happen is that you will not be able to saturate the output signal. You will just stop earlier. So you will have to calibrate your device and the readout of your device to take into account that you've not reached the top saturation of the signal. Anyway, going back to what happens with TIP germanium, you see in this graph that it responds very nicely, very similar to TIPS-pentacene, but what is interesting is that the mobility is a little higher, and what is interesting is that the sensitivity, which is calculated as the slope of these curves, so it is the photocurrent measured as a function of the dose rate. So one varies the dose rate, and that is why we have all these curves that we always acquire. So we change the dose rate, and then we plot the delta I over the dose rate, and the slope gives us the sensitivity. The sensitivity, you see it quite clearly, is much higher for the TIP germanium than for the TIPS-pentacene. And you see it in number down here. So there is quite an interesting difference just obtained by simply changing the one atom in the molecule without changing the structure of the film. Now, that is very interesting because it allows us to further increase the sensitivity of these devices. But what we think is really interesting is not just the record values, which is really good, but the idea that we think we have a way of controlling the way these film and these devices can work. That is another very interesting figure of merit, which is the limit of detection, which can be of interest, again, for certain application. If you want to use the detector under a strong proton beam, of course, this is not an interesting issue. But if you want to measure small contamination, that is important. So how do we measure the limit of detection? We decrease the dose rate, and we measure basically what is the minimum detectable signal that we can reliably obtain and reproducibly obtain. And the message is that we get a very good limit of detection that is reported here, which is extrapolated from this curve. You see, this is again the dose rate going down. And the lowest detectable dose rate is 1.66 or micrograde per second, which is less than the required or standard dose rate delivered in a standard X-ray diagnostic scan. So we're not talking about devices that are so far in terms of performance with respect to those that are routinely used in medical application. Here we go with the response time, and that is what I wanted to mention before. So that is the on-off with the very, very fast on, as you can see it here, response of a TIPS-pentacene thin film. What is the on? The on is a beam which has a higher energy, about 70 kilovolt, and at the time of the on pulse is 100 milliseconds. This machine is, this measurement has been carried out in a hospital under a CT scan. So to test if this device could reliably at least be used to monitor very fast pulses. And it does, because you can see, you can detect clearly the signal, even though the sensitivity is much lower because you're not collecting all of the charge. So there's a trade-off. You can get either a fast response or a high sensitivity, and again, it depends on the application you target. We tested, just for completeness, other molecules where silicon and germanium had been exchanged, and here is the result with diF-TES-ADT and diF-TEG-ADT. And you see that you get same mobility in our thin films, but very, very different sensitivity. So the same films with similar mobility have about more than an order of magnitude difference in terms of sensitivity to X-rays, stressing how the change, the swapping of the silicon with germanium is indeed a very important issue. And again, note that here the mobility is identical. So it's not really a matter of charge collection, but really a matter of absorbing and attenuating the X-rays. So to conclude, we believe that small molecules tailoring is a strong, powerful property of organic small molecules that allow to change the property of the thin films, so to tune them exactly for the applications required. In our case, the X-ray detection can be dramatically changed by simply changing one atom. Of course, we're now working on changing other atom, adding a bit more IZ atoms, and also controlling, of course, the morphology and the shape of the films. I would like to acknowledge all the co-workers and the funding, and you for your kind